is of science faculty. And I've forgotten what you're going to
Doesn't
talk
matter.
about. It's optimal control. Introduction to optimal control. That's basically.
Okay, thanks. I shouldn't thank. I'm also part of their organizing committee, though I don't do anything for them. They both of them organize basically this entire program. And so thanks to you both. And since you are going to have very heavy lectures next 2-3 weeks, I thought I will restrict myself to the very introductory talk on optimal control. Basically, I don't get into the difficulties of optimal control problem. And so those who are already had a course on optimal control problem, you may not be getting anything from me in these talks. But the end of it, the last 2 lectures, if I want whatever I wanted to cover on optimal control, and at the end of last 2 lectures, I want to give you a basic introduction to especially the Hilbert uniqueness method is one of the method to study the linear wave equation for the controllability. I hope I can do that. So this 3 to 4 talks in the beginning is basically a historical talk. So you will get a feeling how this optimal control problem came up, starting from the optimization theory, and then the calculus of variations, and eventually optimal control problem. And eventually, at least, I want to state the Controllability maximum principle and the dynamic programming principle and the Hamilton-Jacobi equations to state. I will not be proven there is a, because this do not come under the way you study other partial differential equations using distribution theory, because distribution theory is basically a linear theory. But the Hamilton-Jacobi equations is highly nonlinear, and the distribution theory do not apply to Hamilton-Jacobi equations. There is a new concept of solutions called viscosity solutions, much later developed, probably 1980s, and probably Shaiju or somebody will introduce what is viscosity solution. So at least I want to state up to that one. So this is a kind of historical thing from 1700s or 1750s from Euler, Lagrange, Fermat, and all that people, and then coming to Pontryagin and Bellman from US, and then it took over by many people, and that's the place I will stop it. So basically, I want to start with something like what is called the finite dimensional optimization. Finite dimensional optimization. Basically, what I want to this is those who, some of the students I'm sure may not have heard any course on all of you had a course on optimal control theory? How many of you have not had any course on optimal control theory? Okay, there is a majority. So it justifies my talk. Okay. So I want to introduce the basically here the concept of Lagrange multipliers. Goes back to 1700s or 1740 or little later. And then the infinite dimensional optimization. What is called, we call it calculus of variations. I want to derive, I do not derive, but I will give you something. What is called at this stage, what is called the Euler-Lagrange equations. This I am sure you had a course, those who have done MSc. I am sure you would have seen this Euler-Lagrange equations and the corresponding Hamilton's form equations. It's a Hamiltonian formalism. Here you will get second order equation for your trajectory. Here, whereas you get a first order system. Okay. And from there, I want to see this calculus of variation, how naturally leads to what is called the optimal control problems. Especially when you study calculus of variations with the constraints. So if you study the calculus of variations with the constraints thing, constraint will lead to certain free variables, and that free variable you can think it as control variables, and eventually you will get that optimal control problem and general thing. And that's where the drastic step from here to here. And the entire analysis is quite classical here. at this stage. It is a smooth analysis. You do that. And it is done in 1700s or 1800s, that period, 200 years back. But then basically, the moment it came to here, from the calculus of variations to optimal control problem, the classical techniques to derive your Euler equations is no longer possible to justify to derive the corresponding equation. And that's where, so from the 1700 it took really a big jump where you need to develop the correct mathematics, and the development started beginning in the 1950s and 1960s. And the development of non-smooth analysis and the development of viscosity solutions are all took place here. So fundamentally, here we want to see that there will be two schools of thought started at 1950s and 1960s. One is due to Pontryagin, and he basically derived that is called a Pontryagin maximum principle. Maximum principle to obtain optimality condition, basically the necessary conditions. Okay, and that has to be justified, and that was actually, and after 19 became, so it's basically a non-smooth analysis is what you require there, and from there onwards, optimal control theory became a distinct field of research. It's gained its own identity. At this time, this was not a separate field. The whole issue was to solve problems which are familiar to you from the science and engineering. You have some standard like John Bernoulli, Euler, and Galileo. Many people contributed, Lagrange, Fermat, everybody. So you have the classical problems from science and engineering. So trying to treat the problems in an individual basis. You have a problem, you want to solve it. So that was the kind of studies, not kind of uniform. So that is where the Pontryagin, so the thing from here to here is a big jump, and new mathematics was required to study the Pontryagin maximum principle. Some of them, if possible, some of them on the way, we will try to point out. The second thought was, this is due to Pontryagin in US, the Soviet Union at that time, and the second one was due to Bellman. It's more or less around the same time, and his view was to see this optimization or the optimal control problem in a more general way, in a generality. And then as you know that if you want to understand basically a function, the best way to understand that function, not just at one point, you also try to understand the function in the neighborhood of that point. So when you study a minimization problem, which you come to that, and minimization starting from one initial point at one initial time, the generalization is better to view that minimal value as a varying function of initial time and initial thing. That gives you to understand better way of understanding the what is called a value function, which will the minimum value view it as a value function of the initial time and thing. The moment you do that one, he eventually lead to what is called the Hamilton-Jacobi and Hamilton-Jacobi-Bellman equation. Hamilton-Jacobi for the calculus of variation, or Hamilton-Jacobi-Bellman equations. Okay, so it's a PDE. So the Pontryagin principle gained significance is a necessary condition, but then engineers were happy more with the Pontryagin principle. They had a place now to where to look for your control, which you can use that necessary conditions, which gives you a class possible optimal controls. You can look for that, and you can use that to construct your feedback laws. And that's what engineers do. On the other hand, Bellman's idea of viewing the value function as a function rather than just at one point, and viewing it as a solution of partial differential equation has a much bigger theory. That the moment you have a much bigger thing, it also comes with difficulties, because you want to treat the value functions which no longer going to be smooth are solutions of partial differential equation, highly nonlinear partial differential equation, and studying that highly nonlinear partial differential equations. So it took much more time than Pontryagin principle to understand this Hamilton HJB or HJB equations. Okay, so and it also provided the sufficient conditions for that. It is, and then there was a connection between the the Hamilton-Jacobi equations and Pontryagin equations. Okay, so with all that, if in these 3-4 hours, if we can cover some of these concepts, I want you to familiar before others coming and talking to you. This is Pontryagin principle, this is Hamilton-Jacobi equation, this is the optimality. Get familiarized with all that in these talks. And maybe one example, the famous example of engineers, the LQR if possible, that's a linear quadratic regulator problem, and which can be applied to this one. And because of the simplicity, because you have the linear dynamics and quadratic cost functional, it reduces the problem in a much simpler form and leads to solutions of Cauchy equations. I'm not sure I will be able to do that one. So this is first 3 to 4 lectures. I want to bring you some of the ideas of that one. There are a lot of notions connected, associated or parallel to that one. Some of them you will see in these coming weeks. One of the thing which you may not see at all is the differential game. It's a parallel development. Differential games. In particular games, and all of you know that game theory is the one John Nash got his Nobel Prize in economics. So there will be more general than optimal control theory, in which there will be more than multiplayers. In optimal control, you can see that there will be only one person who is applying the control. There will be multiplayers like financial market and other areas. But all these, there is one more point which I want to tell you. This 1950s also due to motivator, especially applications from aerospace time. That's what really motivated Pontryagin and Gilbert to look for, especially after the World War II and the aerospace applications. And differential games is also from the defense applications. It's motivator, not differential games, at least the game theory. So there is a parallel. And the other thing you may quite a bit you see in this lecture is the stochastic version of that one. So probably she gave some talks on stochastic to understand the stochastic version of that one. You will get a second order equations and all that, because there will be associated Wiener process with it, and you will lead instead of Hamilton-Jacobi equation, you will get this will be a first order equation in the stochastic version. I don't know whether anybody deals with the second thing. Okay. Anyway, you will have a much more wider and useful theory through the stochastic. So this will set you a stage for that. And I don't know how far you can see that. And the another notion is what you quite a bit you will see a large amount of lectures will be what is called the controllability. That's what you are going to mainly see in this talk. What is this controllability? That you will see as you go. When you go for an optimal control problem, you are basically applying control, and you are starting from an initial point and you are trying to reach at a final point. We'll make more elaborate on that one. And then you will be many paths, many trajectories according to the control. And what you will be using is that you want to find the best trajectory according to your certain criteria called cost functional or the profit, whatever it is, cost functional. So the question is of controllability. What's the guarantee that there is a control for which the system will go from here to here? Or maybe the initial point may be in some set and the final point may be in some other set. So you want to know if you have a dynamical system in which you can apply a control, does there is control which takes the system when it's evolved well according to the control, whether it will reach there. So the question of controllability is a non-trivial issue. This is called basically the controllability. And it's a non-trivial issue, and there is no guarantee that you will have the control. If possible, I will just state in the finite dimensional system the famous Kalman condition in the 1960s, and probably the first step towards studying controllability. It's okay. Finite dimensional system means the moment I say finite dimensional system, the dynamics is an ODE. But then more non-trivial examples comes from PDEs, especially wave equation, heat equation, and also the fluid flow equations. So one of the interesting work or fluid flow. Intense work going around the world is about the controllability of the fluid flow, especially Navier-Stokes equation or stochastic Navier-Stokes equation. I'm sure you will see plenty of lecture on the notions of controllability of Navier-Stokes equations in the next 2 weeks. What I will try to do, if possible, I'll just take the elementary wave equation and try to give you one method, what is called the Hilbert uniqueness method. I want to just at least give you how this motivates you, the controllability. There will be other methods like variational method, variational approach. Probably in the ODE situation, I'll just try to introduce the variational approach if I do. So I'm not going to prove any theorems here. It's up to you to go and study. Okay. So let me begin with something as much as possible. I have given some notes. You can read like a story. If you are not bothered about the validity of my statements, you can just read that one. To make you awake, one of the probably the earliest problem of minimization comes from isoperimetric inequality. I don't know how many of you, probably you can look into the website, Google, and DDoS problem. I'm sure about that. All of you know it. It's basically an isoperimetric. This is probably the oldest problem of minimization. And Lido was a princess whose her brother was killed by her. No, her husband was killed by her own brother, and she has to leave the kingdom. And then on the way, she was looking for a place to settle, and then had a deal with some landowner or some princess. And he said, okay, you take as much as space which can be taken from a bull's hide. Okay, you can get into the story. And then she was a clever lady. She cut that boundary basically into small portions and took the largest area possible. So basically the isoperimetric inequality, if you are given a curve whose length is L, what's a closed curve which covers the maximum area? You are trying to maximize the area so that the boundary is fixed. And all of you, it's not an easy problem, okay? You know that the quality is available only when it is a circle. That you know, right? Sure, right? So suppose you have a curve whose length is L. What is the two-dimensional figure which encloses the largest area? That's why in Kerala every valley is round, right? It's not square, because you try to see that. When you store the petroleum product, you store it in a sphere, not any other thing. Your water tanks are more cylindrical. That's not the best, but then constructing cylinder is more difficult. But then the next best approximation is a cylinder. Okay, so and this is also true with three-dimensional objects. The largest volume which preserves that one. You can put it into one of these problems. That's one problem which all of you know of. This maximizing this one, optimization problem. The second one is also is what is called a Heron's problem. This is more difficult, but this is a nice problem to ask your young sisters or brothers who are in the 11th standard. Suppose you have a line and you have 2 points A and B. This has very good impact, that's why I want to mention it. And you want to find a point C on this line so that A to C plus C to B is minimum. Anybody knows the solution of this? It's a very nice, beautiful solution, which even a 5th standard student will be, not 5th, maybe 8th standard student. So you would have seen that, right? How do you do that? This is what, this may be around 1000 BC, and this may be also in the BC, but more studied by the Fermat, leads to the Fermat's principle. This problem, this solution is easy. If you have A here you have B here, you want to find the C for the minimum, what you do is that you reflect it here B, okay, and then if you take any point here, if you connect this one and this one, this will be congruent triangles, and hence this distance will be the same as this distance. So if you have B prime here, AC plus CB will be the same as AC plus CB prime, and then the shortest distance is the straight line. So you get the shortest distance, you reflect it and then connect A and E here. So this will be the, this is what Fermat leads to the light travels, right? Fermat principle is basically about the light travel. Light doesn't take the shortest path, so light always takes the shortest time. And the law of reflection and law of refraction, eventually the Snell's law in physics are the deductions from here. Okay, it takes the, and that's how if you have an inhomogeneous media, the Snell's law predicts how the light travels. It takes, try to reach everywhere the shortest possible way. Okay. There are other problems, but these are not, these of course is an interesting problem. There are many problems on the way. I will try to say the famous problems which motivated the calculus of variation. The one problem all of you know is Brachistochrone. Maybe we'll tell later, little later. And there are problems due to catenary problem. Some of them I'll explain. And there is another interesting problem, probably is called the Dirichlet principle. And probably, if I understand correctly, Dirichlet principle is look for this best surface so that certain integrals are minimized. But then this is the principle eventually led to people like Poincaré to look for the minimization. So you basically, I will tell that one, basically you are minimizing some gradient functional and you are trying to look for the minimization of such gradient functional. And this is the motivation eventually to study the Sobolev spaces. That's why Sobolev spaces came off much before the actual theory of distribution. And today he is giving the lecture exactly without appealing to the distribution. You can actually give your Sobolev space definition without all that. So, and all the Hilbert's problem of existence uniqueness, all really probably quite bit motivated from the Dirichlet principle. There you try to look for the minimizing sequences because it's a classical time where look for minimizing sequences in the classical space. So the school of thought developed due to Poincaré and other is look for sequences not with respect to the classical space, look for sequences with respect to the norm of something like that. And then you know that this is a problem. That's what eventually you are looking at your H1 spaces, right? We'll try to explain little bit as we go along when you want to do that. There are other problems like action principle, which leads to what is called, even in a special action, you will get your Newton's law of motion. So if you take the correct action principle, where the Lagrangian is your kinetic energy and the potential energy, and if you minimize that one, you will get your, basically the Euler-Lagrange equation will give you to, but this was much more general, not just restricted to that one. If you have any type of Lagrangian of that form, it will get that one. So some of them quickly, without any details. Okay, so let's go to quickly some of the finite dimensional optimization. One problem all of you are familiar, I'm sure. What is the one minimization problem you study in your +2? Probably this, not +2, maybe +3. This one, right? Suppose if it's a continuous function, you want to understand this x is in AB, right? That's all of you know. Actually, we are looking all generalizations of this one. Then immediately you know that when do you have it, when it has a minimum, and when can you characterize it? Can you, if not characterizing, at least can you give a necessary condition? So the first theorem, of course, and that's fine. Then you know that if f is continuous, you have a minimum. That's what you study it. And then you know that if f is differentiable, then you know that a necessary, this is what is called a first order necessary condition, you see. So you are looking for such conditions, but then you will be doing it in a, not in something like one dimension. You will doing it on a, this will be a functional and this will be a class of functions. And you are looking for some sort of necessary conditions. This is what you do it, right? If you want to solve it, to prove mathematically this is fine, but in the actual physical engineering problem, engineers will not be happy that just you give an existence theorem. What you have to give is that you have to give some sort of optimality condition from which you will have a place to look for your solution. The theoretical result may not give you that. But then actually to prove you indeed need a theoretical result. And this is what the mathematicians and engineers science should come together to work on that one. And then you also know the second order condition, right? And if that is positive, it's a minimum. It's a negative, you have that. But you see, if I change a little bit from this problem, slightly to more, and that's what the difficulties you will see in general nonlinear analysis, those who know linear analysis. You are interested in studying, I don't want to replace my minimum. Yeah. The moment I replace AB by R, you have a problem. You are not sure it has a minimum, it has an infimum. And even if it has an infimum, you are not sure whether you can take the minimizing sequences properly. And this is a problem with your nonlinear analysis. So typically you will have this 2 or 3 special cases which you will see. You will suppose you have a function like this. Typically this classifies this and you will have a function something like that, asymptotically goes. And then these are all entirely some different classes of functions, you see. All these functions, infimum of f is 0. You have an infimum. The question is that does that has a solution? You understand when I say that infimum has a solution? I hope that all of you follow. When I say that infimum has a solution, there exists a point x0, this infimum will be f of x0. Otherwise, you see. See, look at here. This graph, typical graph. In this typical graph, all these graphs infimum is 0. That I have stated. But look at here, how do you attack this problem? Even in proving that AB, how do you attack theoretically? You look for, use the definition of AB, look for a sequence so that it converges. That's the way you prove it, right? If you take this problem, if you want to solve this problem, infimum of f in AB, you want to do. How do you take? By the definition of infimum, you know that there is a sequence here, and that sequence of xn converges to this alpha, and then see that xn is in AB, you derive a convergence subsequence, right? And the moment when you go to R, the notion of there is no compactness, you have a problem. And typically you have this case. See, this problem has an infimum, and every minimizing sequence will go to that minimum. On the other hand, if you take this picture, you know that there is a minimizing sequence goes to that one, but I can also take xn tends to infinity, which does not go to a solution, does not give you. So you are trying to construct the solution just by minimizing sequence, you may not achieve that one, you see. On the other hand, all these minimizing sequences does not lead to anything. So the moment you change a little bit, you have a difficulty. And these are some of the difficulties you may come across that one. So this is what the first theorem regarding first theorems probably you can do theoretical result is due to Weierstrass. I think it's due to Weierstrass that when it is AB, it has a, so I don't write it, let's note that. In this case of AB, it has a solution with the other assumption, correct things are given in the notes. Under the assumption that f is continuous. You can prove that. Go and try if you have not seen that. Second case, if f is continuous and f cohesive. So you see you need correct assumptions now. What is cohesiveness tells you that fx tends to plus infinity as x tends to. So you have something to go into infinity. In that case, it has a minimum. Then you have the Fermat's necessary condition, right? If you have more smoothness, something like C1, then and x naught is a minimum point, then you have this. I didn't realize that, but since this year all of you know it, write down the appropriate thing. So you have that one. So you want to do this kind of things for more general setup. That's what calculus of variations doing it. But you know that even in R or Rn, things are difficult. It's not that easy even for R if you don't have the right theorems, right assumptions. This can be generalized even more to Rn. Okay. So you have your unconstrained, what is called it, unconstrained optimization. You are looking for an optimality conditions in the unconstrained optimization. That means f is appropriate. All smoothness are assuming. Okay, when you go to optimal control, you don't have that one. But then that's not a point here, I'm going to say. Because you need to, if you want to understand optimal control theory, you have to take at least one full course. Or you have to read the right books to understand that. Okay. Suppose in the unconstrained thing you want to minimize. If x naught is a minimum. Because there are no constraints, if x naught is a minimum point, that means you have an infimum point has a solution, then you know that gradient of, so the same result I am writing. The same result under the smoothness, you see that you can prove this. And you get, this is called the first order condition, first order optimality condition. You can also derive second order optimality condition. Second order. You use Taylor's expansion or something like that. If I write it, I think this is correct. X naught d is greater than or equal to 0. You can also get sufficient conditions if you strengthen the second order condition where this matrix is positive definite. So you can get back even the sufficient conditions in that. So you can derive that. Of course, this requires more regularity. What is, I just want to tell you some idea, because these are ideas of calculus of variation, or these things are still used. But how to use it in a smooth, non-smooth case is the issue which Ponderagen faced. And the mathematicians from the Lagrange and Euler from to that couldn't achieve that, more difficult things. The basic idea of that, whole idea of that one, if you have an x naught is the minimum, then you take any variation in the neighborhood of that. How do you take variations? You take any vector d in Rn and alpha small. Then x naught plus alpha g will be near x naught. And then x naught is the minimum and you will have this function. If you define as a one variable function, I can apply the one variable theory g alpha, and I am basically varying along that direction. Okay, because this is unconstrained, so I have the freedom to move in any direction, any n direction I like it. And then this is a one-dimensional thing, and g, when alpha equal to 0, g has a minimum, you see. And this will give you g prime of 0 is equal to 0. So if you compute your g prime of 0 or g prime of alpha, you get your gradient of f at x naught into d, not xg. X naught, what do you get it? G prime of 0, g prime, g prime of 0, yeah, you get that. I don't want to compute and spend time. You do that too. So that gives you that the gradient of f is orthogonal to every vector. So you get the proof. That one. Okay. So that's the kind of idea immediately used in that one. But then when you go to the constraint case, you are not minimizing. So you have a minimum Rn, you have f is defined in Rn, and x2 is the minimum point, but you are not minimizing in the entire neighborhood. You may have a surface going through that point x0, or you have something like that. It may be a k or k-dimensional plane passing through that minimum point, and you want your minimum to achieve on that with respect to that constraints. So let's look at a simple example in this case to motivate you. Suppose you want to minimize fx equal to x square plus y square. Of course, the minimum is 0 in that case, that's not a problem. But I want to minimize f. So I'm not minimizing for all x in Rn or something. I want to minimize with y constraint set, say y equal to x plus 1. So I'm not minimizing in the entire R2, rather I mean, what is the curve? This is the shape, y x equal to 0, y1 x equal to, yeah. So I want to minimize f only on that line. Okay, I don't want to minimize the entire thing. What would be the minimum? It's no longer going to be 0, right? The earlier you got at 0 and the minimum value is also 0. But this case it's not. So there are two methods. Essentially the ideas are same in both methods. But the first method may not be easily applicable when you have a surface. That's a thing, general manifold. If it is a hyper or plane or some k-dimensional plane, there is no problem. You may be able to, even then it may be difficult, but if you have a surface, you will have difficulty. But let's do the first method, what is called a reduction method. What do I do is that the reduction method is that I reduce the variable. Since it's in a nice form, I can reduce it here and I can introduce this f of x, y. So I reduce it, g of x is equal to f of x, x plus 1. You see, this is x square plus x plus 1 whole square. So it's a one-dimensional problem in that case. And so we reduced and you do that one. And you can find that x equal to, I don't know, maybe a minimum may be achieved at minus half. You do just g prime, you do get minimum value is probably it's achieved at this point. Okay. So you can quickly do that. The second method is what the real thing, which all the entire eventually the basis to start with your Pontryagin principle. Though it's difficult, the principle of Lagrange multipliers. You this eventually gave that. What do I do is that in that thing one, instead of reducing the variable, I'm going to increase the variable by adding the constraint with a function. So I will introduce a new function with a new variable lambda, and then I will introduce f of xy, in this case f of xy plus lambda into that constraint y minus x minus 1. You see, and view my f as a function in R3 to R, and I try to minimize capital F without a constraint. So minimizing now f over R3 without any constraints. Then if I apply this problem, so this is valid for an unconstrained problem. Okay. Now it's an unconstrained problem. So immediately why this works well, if you take, so if I try to do it, that this condition will reduce to df by dx, df by dy and df by d lambda. You see, you have to have three conditions, capital df by dx, df by dy and df by d lambda. All this is 0. This is what you have to solve it. But df by d lambda immediately gives back your constraint, you see. So by taking the third variable, the corresponding derivative, you get back your constraint. And then you can minimize thing, you can get back the same minimum value, and you will also get a value for lambda. And that lambda, in this case, may be lambda equal to minus 1. This is called basically the Lagrange multiplier in this simple problem. So we want to develop that Lagrange, the whole idea, want to develop this type of thing for the unconstrained problem in the general setup. So you can actually, to understand better way, First you start with the linear constraint and see what information. You are no longer going to get this one, because how did we derive this one? This we have derived, if you, that's why I introduced that method. You got this one for all D in Rn, and this is what implied this one. This is what, and you are not going to, you don't have the freedom to choose here, okay, because now there is a constraint. So if you constrain and if you take an arbitrary direction, it will not retain in the constraint place. So for example, if I take in this example, if I take a direction, if this is somewhere is the minimum, if I take a different direction, it won't lead to that one. So you have to have you don't have this for all directions. Okay, hence you are not going to get this one. So what information, what optimality condition, or you can derive it. So this is called the optimality condition for that. And also there is a problem when it is a constraint problem, when it is a boundary of the domain, all that. Let's not look into that. So let's look at the easy case, linear constraint. How does a linear constraint look like? So a linear constraint, you can write it as the one way to write any linear map is that you suppose it's a dimension k, then you look for a basis, right? U1 etc. uk. Look for the subspace of k dimensional subspace and translate it. And you want that plane to go through the minimum point. That's where the constraint. So you every can be written as x is in Rn with x is of the form something like x naught plus some ai ui. So that will give you an affine plane, right, from the k dimensional space to that one. So the same method 1 and 2 can be applied. If you apply the method 1, what you do basically, you are trying to do here is that it's a plane, so it's easy. What you will get is that you can reduce, because you can reduce the variables here easily, and you will get an optimization problem without constraint in Rn minus k. You see, so if you reduce that k constraints to that one, you basically get a problem in Rn minus k. And what I want to leave this as this, which you can work out. So this will eventually, if you write this equation in Rn minus k, because it's an unconstrained problem in Rn minus k, what you will get is that gradient of x naught ui will be 0 for all I equal to 1 to k. Which is a quick thing, there is nothing. You don't need any extra serious mathematics to do that one. You reduce that one, you can apply it here and do that. So what does this imply? This implies that gradient of fx naught is normal to the plane, normal to the plane here. And that's the optimality condition which you will get it. You can apply the Lagrange multiplier. So let me write at least one theorem. At least for every lecture, at least let me have a theorem. Okay, so that is what the existence of theorem Lagrange multiplier. Okay. Suppose f is probably C1 or C2. If you have C2, you will get second order condition. If you have C1, you will have only first order condition. And if you have the smoothness, you have a second order condition. If the second order condition, you have a strict inequality, you will also have a sufficient condition. All that I am not going to state. I will state only for the C1 of Rn. So it's always a necessary condition. We are looking at it initially. And x naught is a minimal, extremal point. Minimal point. Then there exists Lagrange multipliers. In the nonlinear case, I will try to give you, so that will cover this also. I'll give you try to give you a geometric proof. but then you can give an analytic proof using implicit function theorem and other things. Lambda 1, etc., lambda k, minimum point with the constraints. You need the constraint, it's a problem, right? With constraint given by some, say, n constraint gi of x is equal to ci plus sigma something like bij. You can write linear constraint in this way also. Okay. So I equal to 1 to k. So you have k linear constraints. I am writing the linear constraint in terms of the vectors. If you write down the vectors, you get b vectors. Okay. I equal to 1 to k. So you have k linear constraints. So you want to minimize f, and the minimizer should also satisfy these constraints. Okay. Then he said that there exists a Lagrange multipliers lambda 1, etc., lambda k, such that the augmented function, I am writing what the problem I have given you in one dimension. In the general n dimension, I am writing the theorem. Augmented function f of x equal to f of x plus sigma lambda I gi of x I equal to 1 to k. You see, you augment the constraint to the thing with that satisfies gradient of f at x naught is equal to 0. So you have the existence of the Lagrange multiplier. Okay. You can do that. It's just exactly like one dimensional thing. You can, as I said, you have the second order condition. You also have the sufficient conditions if you have smoothness and assumption on the invertibility of the its derivative. If the derivative is positive, definite, you can write down. So when it's a nonlinear thing, I just want to have few points on the nonlinear thing. How you go ahead with the nonlinear thing quickly. So suppose you want to minimize now again f, minimize f over the constraint over a surface now or a manifold, you can call it surface or a manifold, which is given by k constraint. This is not linear now. h1 of x, etc., hk of x equal to 0. So you don't have that kind of linear freedom anymore. And you want to know how do you, can you get the same type of results and things there. You can do get it. But how do you do that one? That's the problem. So you have Rn and you have the, you want, so assume x naught is a, always you are deriving the necessary condition. I said this is the optimality condition. So I always assuming that this has a solution. Proving that itself is another factor. I'll tell you that's also important. So when you deal with practical problem, you also need that. But as I said, you may not be able to prove all the time the minimizers. If you don't have the right property of J, you will not be able to prove for the minimizer of J. So what we are deriving is a necessary condition. I assume x naught is a minimizer. How do you do? See, what was the idea earlier I had given? When you start with an x naught, if there is no constraint, you can vary any line you like it. If there is a constraint which is a plane, you can vary along that plane. Only that plane where you are the constraints. But still it is in the straight lines. So you start with an x naught. You always look for x naught plus alpha g. If there is no constraint, d will be arbitrary. If there is a constraint, d will be a direction which moves along that k-dimensional space. Now you can't do that one. So you have a point here and it may be a surface. So you have to vary this if you want to construct the one-dimensional variation. You have to look for curves moving along the surface. Suppose you have a sphere and you want to minimize something, and then you have to look for curves there. So you have an x naught here and you have a curve here x alpha. So let x alpha be a curve. Be a curve for alpha small, which such that x0 is equal to x naught. So it's a curve on the surface, and then in the you have to, it's a local analysis. So you look for the curve. So since it is a curve lying on the surface, you have all these property. Hi of x alpha should be 0 because x alpha is a curve on the surface. So it will be 0. Okay, and then you look for the variation of f of x alpha. You see, so that if it is a curve here, so looking for this one dimensional, it's still a curve, it's not a line. So you are having x alpha here. So alpha varies from some say minus some epsilon to epsilon. You will get a local curve here, and you have that one. And if you introduce g alpha here, and still g alpha has a minimum at alpha equal to 0, now it's a one dimensional thing. It's no problem. And g prime of 0 is equal to 0. You see, you still have that property if you move along that. So, but what is g prime of 0? G prime of alpha is nothing but a gradient of f at x naught, x alpha, into dot product dot x alpha. You see, if you do the multi-dimensional calculation. Okay, so you get g prime. So what would be your g prime of 0? Your g prime of 0 at x at 0 is x naught, so you get x naught into x prime of 0. But when you have a curve on a curve lying on the surface, what is x prime of 0? Can anybody tell me? What does that x prime of 0 represents when you have a curve lying on a surface? It's a tangent, right? So since it's lying in the space, it will be a tangent at the point x naught to the surface omega, if I represent. So it's in the tangent space. So basically, all the tangent vectors, basically you can get it from here. You can get your tangent vectors, or you can generate your tangent vectors by looking at the curves in the neighborhood of x naught, all possible curves. But I want to write it. So what I have got is that gradient of f at x naught for a tangent vector is 0. This is what the optimality condition I have got it. But I want to connect it with hi. Then only it will be a good one. So far I don't know. Right? So I want to understand. Of course, those who already studied a bit of differential geometry, you don't need much differential geometry. The first step in the differential geometry, when you study, you will know what it happened. You can apply this kind of same procedure to these kind of things because you have 0 here, not because this is 0, but this itself is 0. You can do an analysis there. You will also get gradient of hi x naught acting at x prime of 0 is also 0 for all 1 less than or equal to I less than or equal to k. So you see, for all those tangent vectors, you have this one. But then there is a subtle and very minor exercise. Every vector satisfying this condition will be a tangent vector. That you are required to prove. It's a minor proof, but you can do it in the exercise. What I am saying is that if gradient of hi x naught of d is equal to 0 for all 1 less than or equal to I, then d is in the tangent space. dx star. So now we can rewrite the condition here. What is the condition with this information? These two information will tell you gradient of f at x naught d is equal to 0 for all d such that gradient of hi of x dot equal to d equal to 0. Okay. Now you can forget your differential geometry because nothing is coming. It's only vector and algebra is coming. So the condition you reformulated as the optimality condition, you have reformulated as that if a vector is orthogonal to every vector gradient of hi, then that's also orthogonal to d here. Yeah, I want to make one more assumption here. It's indeed a k-dimensional space. If I am just given k conditions, that doesn't mean that it's a k-dimensional space, right? I can have an independent, if it's dependent, it will not give you to k-dimensional thing. So basically you have to assume, so that's a necessity here. Assume the set gradient of hi, maybe x naught is enough, 1 less than or equal to I, less than or equal to k, is independent. Geometrically, You feel that one? If you want to give an analytic proof, this is the one you have to do, need it to apply your implicit function theorem. This invertibility of this vector will eventually tells you that you can solve your other vectors, n minus 1 k vector from that in terms of k vector, and the concept of reduction can be done in principle locally. You see, you have given that one, the same principle of reduction in a neighborhood of that, which can be done. Okay, so this tells you that with that one, so if you have a vector which is orthogonal to here, then it will be orthogonal to this vector. It shows that this vector will be in the linear span of gradient of Hi. That's what the information. So your gradient of f at x0 is in the span of gradient of Hi. 1 less than or equal to I less than or equal to. And that's the Lagrange multiplier theorem, right? That means gradient of x0 can be written as a linear combination of gradient of Hi. That coefficient is lambda 1, lambda k, etc. In other words, there exists x0, etc. I equal to 1 to k, lambda I gradient of Hi. When Hi is linear, you know that it reduces what you have done earlier. So that gives you the concept of Lagrange multipliers. I'll give one quick example how this helps you, one of your well-known thing, and then maybe continue after G. Okay. Just one example. How this both can be applied, unconstrained and constrained, to an eigenvalue problem. Suppose you have a symmetric matrix. A. Symmetric matrix. A. With eigenvalue lambda and eigenvector x0. Then immediately you know that lambda is nothing but ax0, x0 is the dot product, ax0, x0. Normalize it. So you have your lambda. If lambda is an eigenvalue, you have that one. So this motivates the notion called Rayleigh Quotient. So I can define now a function, what is called the Rayleigh Quotient, Rx. For every x in Rn, x not equal to 0, I can define the Rayleigh quotient. Rx equal to Axx. This is real because it's symmetric, right? So that's no problem in the definition. The question is that can I get back my lambda or x0 as a minimizer of this one? Can I minimize Rx in unconstrained minimization? Can you get back my R? And you can apply this theorem quickly and you can compute it. It's enough to compute gradient of Rx. Okay. You will have some factor. I remember it's there in the note. But what you will get is that after that you get Ax minus Rxx. You compute that because this is a n-dimensional thing. You can immediately compute. Please go and do it today because you have to stay here for 3 weeks, right? So it's nice to evenings spend some time. Okay, and also you have to listen to me tomorrow also. You see, so better come with go through that. Okay? So there is a coefficient. So and what is the condition? Gradient of Rx not equal to 0, right? So gradient of Rx not equal to 0 is if and only if Ax0 is if and only if Ax0 is equal to Rx0 into x0. So that shows that x0 is an eigenvector and with the corresponding eigenvalue Rx0. So Rx0 is an eigenvector. Then you need to do little more work. You can actually show that in the unconstrained this case, if you minimize that one. So this is for both minimum and maximum it will work. So if you have a minimization problem, you can actually deduce that Rx0 is the least eigenvalue. You can see that in the minimum full unconstrained minimization, this will be lambda 1 and maximization will give you lambda n. But what about the other eigenvalues? So you got the minimum and maximum eigenvalue with the corresponding eigenvector. To get capture your other eigenvalues, you have to go to an unconstrained minimization. Constraint minimization. But you do that the moment you get the first eigenvalue, eigenvector, you look for your solution not in the whole thing. You don't minimize there because you already got an eigenvector which corresponds to the eigenvalue lambda 1. So to capture lambda 2, you remove that eigenspace. You look at its orthogonal complement. So if you have up to k, you have it's a span of the eigenvectors corresponding to lambda 1 etc. lambda k, and look at ek plus. So you are not going to get any more here, and you have to go to in the ek plus. So you have to basically minimize f with respect with this constraint, and then you can go for that. So this is what the Rayleigh Quotient. There are various ways of writing the thing. Minimax or either minimax or orthogonal x is in order ek complement and rx, and you minimize it. So your entire Rayleigh Quotient minimization for this eigenvalue problem. Of course, this is not just one application. You can apply to many things. So I'll continue after T.